Today we're going to explore more in depth the constant velocity model, which we call CVM for short. And the way we're going to do this is we're going to look at a sample data set where we have our two columns here, our time and our location in space at that time relative to a reference point of 0 on our position axes. So we want to look, there are 5 different ways besides this, which is the 6th way, that we can actually represent the motion of this object on the position axes. The first thing we're going to look at is a motion map, where we have drawn our position axes. We have placed our dots at 2-second intervals. So our starting location is our first dot, which is 0, 2, 4, 6, 8, 10 full seconds. At 0 seconds, it's located at position 4, and then it travels along at a constant rate till 10 seconds, at which point it reaches 34 meters. So this motion map directly corresponds to this same data, and from this same map we can get all the same information as what we can get from here. A second way of describing this data is with a graph. Remember that on this graph you now have a position and a time axes. In math you just have an x and y axes. Both of those represent position. In this case we have one that represents a location and one that represents time, which is very different. Time can only ever move forward. It can never move backwards. So that being said, where your object starts is at a time of 0, which is going to be that y-intercept, the initial location, which in this case is 4 meters. Then you just plot out at 2 seconds, it's at 10, at 4, it's at 16, 6, 22, 8, 28, and 10, 34, and then you can draw a line to connect the points. So this clearly shows that your object went from 4 meters all the way up to 34 meters in a time of 10 seconds. So it's the same data as the motion map. A third way of representing this data is using words. So the object started at a position of positive 4 meters and traveled for 10 seconds at a constant velocity of 3 meters per second. We don't need to say where it ended because we know how long it traveled for and at what rate it traveled. So if it started at 4 and traveled for 10 seconds at 3 meters per second, this means that it traveled an additional 30 meters, so its ending point would have been 4 meters. The fourth way we can describe this data is using the equation for the line. And this equation comes from our graph right here. In this graph, we're using the equation of the line, y equals mx plus b. In this case, our y-axis is our position. Our slope we can get, which is rise over run, directly from our graph here, and because it's a constant slope, we know that we can use any 2 data points on that graph to find the slope, multiplied by our x, which in this case is now time, plus our b, our y-intercept, which we know is 4 meters. The fifth way of describing this graph is new. This is a velocity versus time graph. It's similar to a position versus time graph, but on a velocity versus time graph, we simply plot the velocity of the object for those full 10 seconds. Well, we know, since the slope is constant and the slope represents the velocity, then the velocity must also be constant, which means it never changes. So our velocity starts at 3 meters per second and stays that same rate all the way until 10 seconds. Just remember that this doesn't tell you the initial position. That y-intercept is no longer the initial position, it's the initial velocity, because this is now a velocity axis, not a position axis. But this same thing tells you that at time t equals 0, you started with a velocity of 3 meters per second, and at time of 10 seconds, you ended with a velocity of 3 meters per second. This graph cannot completely describe this data set because it doesn't tell you your initial position. The next thing we're going to look at is how to use these things to solve problems. So the first thing we're going to solve for is displacement. So solving for displacement in the constant velocity model. And again, we're going to look at an example. That example was what was the displacement of the object at t equals 7 seconds. So we're using the same data as before. Well, we can start by using the motion map. Find the location of the object at t equals 7 seconds and approximate the location. So we would start and we would look at t equals 7 seconds. So if this is 0, 2, 4, 6, and this is 8, then it must be right in between the two, which would be 25 meters. But this is not displacement. Remember, displacement is change in position, not just position. So the position at 7 seconds would be 25. But the displacement would be that change in position. So our final position is 25 and our initial position is 4. So our change in position would be 21 meters. So at 7 seconds, the object would have moved 21 meters away from where it started. The next method of finding the displacement is with the graph. Draw a line up from the time and over to the position to find the x final. Remember, the x initial is the y-intercept. So we're at 7 seconds, so we're going to draw a line up at 7 seconds, and then we're going to find the corresponding location on the position axis, which happens to be 25. So the final position at 7 seconds is 25, and the initial position is that y-intercept, which is 4. So final is 25, initial is 4, so the total change in position is 25 meters minus the 4 meters, gives us a change of 21 meters. There are 4 ways to find this displacement. The next way is using the equation. Well, plug in the values to the equation of the line to find x final. We know that the equation of a line is the final position equals the velocity times the time plus the initial position. This is our x, y equals mx plus b. We know that our y is the x position at that time. Our v is our slope, so our velocity is our slope. Our x in this case is t, and our b, or our y-intercept, is our initial position. So the formula is x final equals vt plus x initial. We can just move this to the other side by subtracting. So we have x final minus x initial equals vt. And of course, you should recognize that x final minus x initial is the total change in position, or the displacement. So all we have to plug in is our velocity times our time. So in this case, our velocity was 3 meters per second, and we wanted to know what the displacement was at 7 seconds. So we would multiply. The seconds here is on top, the seconds here is on the bottom, so they cancel, and we get our displacement is 21 meters. Last way of finding the displacement. Displacement on a velocity versus time graph is the area under that curve. We know that the velocity is constant, so it's a flat line. So we simply draw a line up from 7 seconds, and then we know that it goes across the top, and the area for a box is length times width. So the length here is 7 seconds. That's how far our line is forward. And then our height of our box here, we know that it traveled at 3 meters per second, is 3 meters per second. Again, this seconds is on top, this is on the bottom, so the seconds cancel out, and 3 times 7 is 21 meters. We can use steps very similar to all of these to find the time on an equation. Or if we know the displacement, we know the velocity, we can simply solve for t instead of for delta x in all these equations to find the time. How do we go about finding the velocity in the constant velocity model? Well, the first thing we can do is we can use the graph. We can use the graph and determine the slope of the line and use that to find the velocity, because we know on a position versus time graph, the slope is the object's velocity. So we can take the slope and we can do the rise over run. And because it's a straight line, we know that that velocity is constant over the entire time interval. So we would use the average velocity, which is the total, or we would use any 2 points. We don't have to use the average, we can use any 2 points. Because it is a constant slope, it's a straight line. So rise over run, well, in this graph, for every 2 seconds, it travels up by 6 meters. So it's 6 meters per every 2 seconds. So the slope is 3 meters per second, which is the velocity. The other way we can solve for the velocity is by using the equation. So the slope on a position versus time graph is the change in x over the change in t, which is the velocity. So for the average velocity, plug into this formula the total displacement and the total time. That would give us the average velocity over the entire length of the graph. And because the graph is a constant slope, it doesn't change at all, then we know that we can use the entire time period, or the total time, the total change in time, 0 to 10, and the total change in position from 4 to 34 to find the velocity over the entire time interval. So we would simply plug in change in position over change in time. X final is 34 minus X initial is 4, T final is 10, T initial is 0, gives us ends 30 meters, and it's over a time period of 10 seconds, so 30 meters divided by 10 seconds gives us 3 meters per second. So we have found another way, using this equation, to find the velocity of this particular object. So if you didn't have a graph, you could just use the equation. If you did have a graph, you could simply solve for the slope. Today's key word shall be displacement. So today's magic word is displacement, and I will see you guys in class. And don't forget that you have your Unit 1 online homework is now open, and by next class period, you need to bring your car lab. See you guys then.